Right. Good morning again, and welcome to this lecture of electronics. Now we were studying diode characteristics or the applications of diodes, in which we have almost completed all sorts of clippers, clampers, rectifier circuits. Today we are going to learn some portions of the derivation part of the rectifier, which I guess we have missed it in the earlier classes. So let me share my screen. I guess my screen is visible to you. Is it visible? Yeah. So let me introduce myself. Hello, am I audible? Anybody can unmute and let me know. So myself,
Yes, sir.
Dr. N.D. Meshram, Head and Associate Professor, Department of Electronics, Sri Mathuradas Mota College of Science, Nagpur. And today we are going to study more about the diode circuits, and they are being used in power supply. And what are some of the derivations which are essential for these rectifier circuits, right? So today we are going to brush it up those things, right? So this is an altogether a different portion that we have studied earlier. Let us start with that. So in this lecture, we are going to study clippers and clampers. We have almost completed. We are not considered about voltage multipliers and power supplies. Yes, sorry, half wave and full wave rectifiers, half wave and full wave rectifier circuits. Uh, then yeah, so we'll be having some derivations of this VRMS, VDC, ripple factor, peak inverse voltage, rectification efficiency in each case, and the capacitor filter. So we have completed almost all. We have to do some derivation portion of it. So I guess from my side, you should have one copy with you and keep on writing, or even you can take some snapshots of it. Okay, so this was the basic block diagram of DC power supply, which we have studied earlier also. So this was the AC 230 volt AC 50 hertz frequency, which was applied to the transformer. It is actually a step down transformer, which is supposed to convert the higher AC voltage to a lower AC voltage. Then it is fed to the rectifier circuits. We are having some rectifier circuits which we study again. So these are the rectifier circuit. The output of rectifier circuit will be the pulsating DC. Then we put this output to a filter circuit. Yesterday we have studied the shunt type capacitor filter, and we still have some. Say, it's not pure DC still. So it is having some fluctuations over there. So that is being controlled or being regulated by this voltage regulator circuit. So this was the block diagram of that. Rectifiers, which are used to convert AC into DC. And on that note, we are having two types of rectifiers: half wave rectifier and full wave rectifier, right? So half wave rectifier getting output in the half cycle of the input signal, whereas full wave rectifier which gets output in full cycle of the input signal. Half wave rectifier. Now remember this, we are going to study in a different perspective. So I'm just repeating it for you. What is an half wave rectifier? So half wave rectifier is a circuit which is having only one diode and which is going to conduct during one of the half cycles, whether it is a positive half cycle or a negative half cycle. So it's going to say conduct or work during that, and during the other half cycle the circuit will be as good as an open switch, and the output across this load resistance will be equal to zero, right? So now in this circuit, the diode is supposed to work in the positive half cycle. During that positive half cycle, this diode will be forward biased and it will conduct, and the positive half will appear across this load resistance RS, right? But during the negative half cycle, it will work as an open switch and there will be no output voltage across this load resistance, right? So we'll be having only half of the wave. To show you the waveform, this is the AC wave which is being applied to this rectifier circuit. And at the output, we are expecting these types of only half of the waves which are supposed to come. And during this half, negative half, the output will remain at 0 volt, right? So remember this. At pi 0 to pi, we are having output voltage equal to Vm, and again from pi to 2 pi it is 0. Then again it will start from 2 pi to 3 pi. Then the output voltage, the amplitude of the output voltage will remain it as Vm, right? So this is very important for as far as derivations are concerned. So what is the first portion of the rectifier circuit? So we are working on, say, the half wave rectifier itself. So the one of the characteristics which is very important as far as diode is concerned, is the peak inverse voltage. Peak inverse voltage means the voltage which the diode will sustain when it is applied in the reverse bias condition, right? So that is called as the peak inverse voltage. So it has some limitations. Beyond some voltage, what will happen? It will break, right? It will get damaged itself. So we have some limitations. We have to make sure that the peak inverse voltage should not exceed this value, right? The definition of this peak inverse voltage is the maximum voltage the diode must withstand during the reverse bias half cycle of the input signal, right? So maximum voltage the diode must withstand without damaging the diode. What would be the maximum voltage during which the diode will remain in the working condition? Still, the diode does not work in the reverse bias condition. It will be as good as open, but it has some limitations. So peak inverse voltage in half wave rectifier should be equal to Vm, right? So that Vm we have seen in the last slide. So this was the highest amplitude, right? So we want that the highest input voltage that is supposed to be applied to this diode without damaging it. That is the definition of peak inverse voltage. It is very essential to know that how much voltage the diode is going to sustain during it is working in the reverse bias condition. Disadvantages: low output because only one half cycle delivers the output. Now this is the disadvantage of, say, the half wave rectifier, right? So the half wave rectifier has the disadvantage of low output because only one half cycle delivers the output. The AC components are more in the output, right? So there is the AC components remains in the at large position. So let us continue with that. Okay, now let us try to analyze the half wave rectifier. Now we will work in the say derivation portion of it. So what is the DC output? So the DC output voltage or a current of the rectifier is the average value of the output voltage or current. Remember the definition: the DC output voltage or a current, DC output voltage or current of a rectifier is the average value of the output voltage or current. That is the average value which is supposed to come across the output. And what would be its formula? IDC or VDC is equal to area under one complete cycle divided by the time period, right? So that is the DC output voltage, and we call it as, say, the average value of the output voltage or current. So this is shown over here. The formula is for the current. So current DC is equal to area under one complete cycle divided by the time period. Okay. So current flowing through the load resistor will be IL is equal to Im sine omega t. Now this is the equation for the sine wave, and since it is written as I, so it is the say it is the formula or say equation for, say, the current. Wherever we have I, it means it implies that it is for the current. So the current flowing through the load resistor RL are equal to IL equal to Im sine omega t, where Im is the maximum amplitude of the current. Sine is the sine angle of the wave. Omega is the angular angle, and t is the time period, right? So at that time we will be having different. So current flowing through the load resistor, that is IL is equal to Im sine omega t. Okay. Now if you put this, that is IL is equal to Im sine omega t for 0 to less than or equal to omega t less than or equal to pi, right? So during this 0 to pi region, we will have this type of a signal. During the negative half cycle, that is from pi to 2 pi, where omega t is supposed to be 0, the current flowing through that is should remain to 0, right? So during this positive half cycle, we will be having this Im sine omega t, and during the negative half cycle, the current flowing through that will be equal to 0. Now, here area, how to calculate the area? Area will be equal to the integration from 0 to pi Im sine omega t into d omega t, right? So this is the integration of, that is the total, or we can say that is the average value of the output current. So 0 to pi, in that region, we are having the highest current flowing through that, that is the positive half cycle. So from 0 to pi, Im sine omega t. So I have put this whole equation over here. We are integrating means we are adding it, and we are trying to take the average value of that current. So if you integrate this, then it will come out to be this Im is constant, so I'm taking it out Im, and the integration of sine omega t will be equal to minus cos omega t, and we have to put the limits. So 0 to pi is the limit, and we'll be having the value equal to, if you put 0, then this will become high, and if you put pi, then sorry, uh, 0 minus pi, right? So cos of 0 minus pi. So cos of 0 will become 1, and cos of pi will be 0. Okay. So the output which is supposed to come will be equal to Im, twice of Im, sorry. So it is the, say, it is the IDC, twice of Im. Now, if you put time period, that is equals to 2 pi. So we can calculate the average current, that is IDC is equal to twice Im by twice of pi, and that is equal to Im by pi. So this is the average value, or we can say the DC output current value of the half wave rectifier, right? So I guess you have understood this much. Do you have any problems in this? Have you understood the derivation up to here? Anybody can unmute and let me know. Even you can send a message. You can chat. So please let me know if you have understood this. This is the simplest derivation. I will repeat it again for you. So we were working on DC output voltage. So the definition of DC output voltage or current of a rectifier is the average value of the output voltage or current, right? And that the equation of that is IDC is equal to area under one complete cycle divided by the time period. So first we need to calculate the area. So for that area, we need to know what is the current flowing through the load resistance, and that is equal to IL equal to Im sin omega t. And when we put that in two halves, that is the positive half and the negative half. So during the positive half, the diode is supposed to conduct. During the negative half, the current will remain zero. So for positive half, it should be IL equal to Im sin omega t for this region. That is from for 0 less than equal to omega t or less than equal to pi. So from 0 to pi, it is going to have this. From, say, pi to twice of pi, it will remain at 0. Okay, so if you need to calculate the area under it, what would be the area? That will be the half of the cycle. So 0 to pi, Im sin omega t into d omega t, right? So we can calculate this by simple integration, say, formulas. So we'll be having this, and substituting the value, will be getting IL, sorry, uh, the area under one complete cycle will be equal to twice of Im, right? So it is twice of Im. Then further, if you do that, so we are having a total time period of 2 pi, that which starts from 0 to pi, pi to 2 pi. Okay, so time period will be equal to twice of pi. If you divide this, will be getting the average value of the current, or say the DC current. So IDC will be equal to twice of Im divided by 2 pi. So again, solving it, we'll be getting Im by pi only. So this is the simplest equation of that. Then moving further, voltage, how to calculate the VDC voltage or DC voltage. So for DC voltage, we can have the ratio of current and, say, yeah. So for voltage, Ohm's law, if you put V equal to I into R, so we'll be having that VDC will be equal to IDC into RL. That is the Ohm's law, right? So voltage DC will be equal to IDC into RL. When you substitute the value of IDC over here in this equation, we're getting VDC equal to Im by pi RL. So that will be the value of VDC. While diode is in forward resistance, that is RD is taken into account. And along with this, RL will be having the small resistance, negligible resistance of the diode when it is conducting, right? So we are taking that forward resistance equal to RD. So the total resistance in series will be RD and RL. I will just go back how this RD is appearing over here. We can talk on that, right? So just hold for a moment. Yeah. So yeah, I need to show that. So what I mean by RD is, the resistance, there might be a small resistance of this diode which we are taking is RD, and if you connect this RD, this small resistance in series with RL, so the total resistance in this circuit will be equal to RD, that is the small resistance, forward resistance of this diode, plus RL. So this is how it comes, and the total resistance will be RD plus RL. I guess you understood this. And this is the region 0 to pi. And from pi to 2 pi, we are having 0. Again, from which will start from 2 pi to 3 pi. And from 3 pi to 4 pi, it will remain 0. So this is the omega t, that is the time waveform over here. And this is how we are going to calculate. So I guess you have understood this. Okay. So this RD by how it is appearing over here. So Im will be equal to Vm divided by RL plus RD, right? So now we are having RL plus RD over here. If you substitute this in this VDEC equation, that is Im by pi into RL. So at the place of RL, we can substitute RL plus RD. Okay. So VDC will be equal to RL by pi RL plus RD. And yes, if you further say solve it, we can take Vm by pi as common. So we'll be having 1 plus Rd by RL, right? So Vm by pi 1 plus Rd by RL, will be having this equation as VDC. So this is the equation for voltage DC over here, and that is nothing but equal to Vm by pi. If you take this as very negligible, 1 plus Rd by RL will be very small. So if you divide this, then it will remain as equal to 1, and therefore VDC will be equal to Vm by pi. So this is the equation for, say, the voltage DC. Again, solving further, what would be the formula for RMS value of the voltage? That is the root mean square value of the effective voltage, that is calculated by the effective value of the current flowing through the load, and that is given by the formula IRMS equal to under root of area under the square rectified wave over a circle divided by time. So that is nothing but the IDC. The square root of IDC will give you this IRMS. So in case of half wave rectifier, IRMS will be equal to 1 by 2 pi integration of 0 to pi IL square d omega t. Okay. And again, substituting it and solving it, will be getting this type of equation. So here IRMS will be equal to 1 by 2 pi integration of 0 to pi IL square d omega t, and 1 by 2 pi 0 to pi m square sin square omega t d omega t. Again, solving it and taking constants as common, we'll be having this. So Im square by 2 pi 0 to pi 1 minus cos 2 omega t by 2 into d omega t, right? So further solving, we'll be having this, and the ultimate equation IRMS will be equal to Im by 2 and VRMS will be equal to Vm by 2. So we won't go land in the further this. Just hold for a second. We are having prayer, right? So for a moment, I will just say stop. Right. So yeah, so we were talking about this. So this is how we can calculate the RMS value. Root mean square is an effective value of the current flowing through the load and is given by this equation. IRMS is equal to under root of area under the squared rectified wave over a cycle divided by the time period. Now, if you substitute this values, so area under the squared rectified wave, that is equal to from 0 to pi, that is 1 by 2 pi integration of 0 to pi IL square into d omega t. Okay, so this must will be the area which is under it. And if you substitute this, if you substitute the value of IL over there, then we'll be having Im square sine square omega t dt d into omega t, right? And again, if you solve it, so sine square omega t can be written as 1 minus cos of twice of omega t by 2, right? So this is the trigonometric formula. Sine square omega t can be sine square theta is equal to 1 minus cos square theta by 2, right? So that is the formula. So if you substitute this, taking out Im square as common, So we have taken Im square common by 2 pi, 0 to pi, 1 minus cos 2 pi omega t by 2 into d omega t. Again, it's by solving. Substituting the values will be having omega t minus sine 2 twice of omega t by 2. And if you put the limits over there, then we'll be having only this much. So the total 4 will be over there. So that gets cancelled, and we'll be having again Im by 2. I have the RMS value, and if you substitute the VRMS, then we'll getting Vm by 2. So this is the RMS value of the total current, which include DC value and AC components in the output of the rectifier. The instantaneous value of AC fluctuations is the difference of the instantaneous total value and DC value. Instantaneous AC value is given by the equation I dash is equal to IL minus IDC. So this will give you actual fluctuation, which is over there. So here the RMS value of AC component is given by IRMS, I dash IRMS is equal to under root of I square RMS by minus I square by DC. So if you again substitute these equations, okay. So this is for the ripple factor. So the ripple factor is another parameter of say the AC wave that we are having. So this is for IRMS and VRMS. Then for the ripple factor. So the ripple factor is defined as the ratio of ripple voltage divided by the DC voltage. The purpose of the rectifier is to convert AC voltage to DC, but not type of a rectifier converts AC to pure DC, right? So rectifier does not give you pure DC. It produces pulsating DC. This residual pulsation is called ripple. So ripple factor indicates the effectiveness of the rectifier in converting AC to perfect DC. It is the ratio of ripple voltage to the DC voltage. So we'll be having this gamma equal to ripple voltage by DC voltage. Ripple voltage is nothing but the RMS value of the AC component divided by the DC component. You substitute this, that is V dash RMS divided by VDC, or gamma can be written as I dash RMS divided by IDC. And again, we can calculate these by substituting these equations. So we'll be having just nearly coming out to be equal to 1.21, right? So this is for, say, the value of, say, the ripple factor. So ripple factor of half wave rectifier is around 1.21. Then if you go for efficiency, efficiency of the rectifier is a measure of conversion of AC power to the useful DC volt output power. It is expressed as the ratio of DC output power to AC input power. So efficiency neta is equal to PDC, that is power in DC divided by power in AC, right? Where PDC is the power delivered to load, and PAC is the AC input power from the secondary winding of the transformer. Here, PDC is equal to I square DC into RL. To substitute, we'll get this. And PAC is equal to I square RMS into RL plus RD. So we'll be having IM square by twice of IM by 2 whole square multiplied by RL plus RD. And again, further, if you derive it, so neta will come out to be, say, around 40.6% if you go in solving this. So this is all about, say, the half wave rectifier. In the next class, we are going to study about the full wave rectifier. So these are some of the derivations that we are expected to know. So this is IDC, VDC, then we are RMS values, and then again for the ripple factor. So we are having this as ripple factor, and this was the value of ripple factor in half wave rectifier, that is 1.21. That efficiency means how much efficiently the rectifier gives you the DC power, DC output, right? So this was the equation for that, and this is the solution for neta. So it comes out to be 40.6% for, say, the half wave rectifier. So I guess this much is enough for today. We'll stop over here. If you have any queries, you can ask me. Okay. So thank you. Thank you very much for joining the class. And I guess you have understood what are the efficiency, ripple factor, and say IRMS, and the DC voltage and current, right? In the next coming classes, we will be working on, say, the same parameters, but Instead of that, we will be working in the full wave rectifiers, right? So thank you very much. Stay tuned to my YouTube channel. Please go through my YouTube channel, watch, like, share, and subscribe my channel. Thank you very much. And by that time, we'll be meeting in the next class. By that time, take care, stay home, stay safe. Have a nice day. Good day. See you in the next class.